Welcome to this talk. The idea behind this presentation is that I have an excuse to go through the books in my bookshelf, and also kind of like to share with you what I read and what I kind of like think about this. So in this case, I'm going to cover designing distributed systems. The idea is to give a rough overview of what the book is about. So the too long didn't read is that we have on these distributed applications that we have been building for, let's say, the last maybe 10 years or so. Patterns have started to emerge, and we can reuse those patterns. We can learn from people that have applied these patterns and from the failures or successes. And yeah, nowadays we think about design patterns and they kind of like get a bad reputation. But maybe it's more like has to do with not applying them properly or going to the extreme and applying patterns everywhere. So it's important to keep in mind, let's say, the trade-off that we're having with these patterns. So we have three, let's say, or we have several benefits for using design patterns, but the book mentions these three. So we have a common language, meaning that we don't have to have I think the book says something about violent agreements. Like we are referring to the same thing, but on a different language, and we don't arrive to an agreement just because we don't know that we are talking about the same thing. We are just using different words. So by having a common language, we improve communication. This is something that also was mentioned on the old design pattern book by the Gang of Four. We also have reusable components. So once we start as not only as an organization, but also like as like in the industry, we start to recognize these patterns. We can factor these patterns into components, into kind of like libraries, if you will, and we can reuse these libraries within the application, within the organization, deploying them in different places, or we can outsource these components so other organizations or other teams can leverage it from. There are obviously some challenges whenever we are talking about these reusable components, because we have to think about if they can be language agnostic. And obviously, yeah, this becomes a learning opportunity as we can understand where other teams or organizations fail while designing distributed systems. And the patterns that the book mentions are on at least on 3 levels that we are going to cover on the presentation. So the first type of pattern that we see are single node patterns. So a single node pattern is when we decompose the application that is deployed in a single node, in a single machine. The idea is that whenever we are splitting this application, we deploy inside the same machine, or for the lingo in Kubernetes, that would be a pod. So within a pod, we deploy multiple containers, and what we do is we have different patterns that we can use, and we can deploy as containers. So one of the things, and I feel like this is a section that we benefit the most. We'll see the remainder of the sections, but this is a kind of like maybe novel to most of us of how we compose applications. So usually it's quite easy to understand when we need to split a system, and whenever we want to say we have let's say maybe some microservices, and we say, okay, this is the front end, this is the back end, this is the part that deals with logins, or this is the part that deals with that. But it's much harder to understand when we need to split out an application by itself. So in a sense, these patterns force us to think about, okay, what's the value that our main application is delivering, and what are the supporting services or the supporting features that that application has, like maybe monitoring or logging, and is kind of like challenging us to think about, hey, what would happen if you would split this part into another container? So if it wouldn't be embedded inside the application, like importing a library, but more like a container that's running besides your application container. So obviously this, as I mentioned, has some challenges and also has some benefits. On the one hand, the idea behind using containers is that we can isolate resources, and we can define priorities within a pod, right? So within a pod, each container has can claim different CPUs, different amount of CPUs, or different amount of memory, and we can be more selective of what the resources that we can give to the pod, and this is an advantage. And also it makes the development teams more focused, because maybe some team is solely thinking about the application itself and the value that delivers for the business. And then there's another team that is developing these reusable containers that are implemented like a sidecar or an ambassador, and they are solely focused on that. So this creates some synergy or some focus with the different teams. So the first pattern is the sidecar pattern. So this is again a container that's deployed in the same pod as the application container, and its purpose is to augment the capabilities of an existing application without modifying its source code. So in this case, we see that the container group, the pod, has an application container, has some shared state or some shared resources, such as the network, the disk, etc. And also we have the container, and there is some communication that happens between the sidecar and the container. So some examples that the book mentions, and let's you think about how we would implement this. There is also some piece of source code on the book that refers to how we would implement this. So, for example, the first example is adding HTTPS support to a legacy application. So it goes about and says, hey, we have this application that's legacy, that has a build system that no one has touched in years and no one understands. So maybe what we can do is we can, by enabling HTTPS support, we deploy, as a sidecar, we deploy an Nginx application that handles SSL, handles the SSL termination, and then forwards the request internally to the legacy application within the same pod. Then another example is
it's also useful in general, and not necessarily for maintained.
Yeah.
You want to touch.
Yeah, totally.
If you have a variety of applications, you can do all of the TLS termination in the same way.
Yeah.
And certificate rotation management.
Yeah, exactly. Yeah, I think that this is more like to prove why would you do it in like kind of like to force you to say, hey, I cannot touch this code at all, because maybe as developers, the first thing that we would say is, okay, let me import this library, let me redeploy it, and it's done. But this is more like to prove the point. Also, well, talking about configuration hot reload. So again, let's say that your configuration works through files or config maps or whatever. We can have a sidecar checking the updates on this configuration, and if there's an update, we can trigger the other application to say, hey, this has changed, you have to reload the application, you have to reload the configuration, and this can happen in different ways. It could mean killing the container or restarting the container, or sending a signal, or triggering an HTTP endpoint. There are different ways to go about this. And then finally, so the first two examples work mostly with, the book mentions legacy applications, but that's not the only thing that that is useful for. So in this case, it mentions that we could certainly add an endpoint So we could deploy a container that gives us CPU information, memory information about the application container using some some top command. So like the Linux top command that we have, we can inspect the process. We have a container that runs this process, or runs this command, and exposes through a REST API or an HTTP endpoint. So that would be one way to do it. So in this case, we can see as an example, we have for the HTTPS implementation, we have some request that is coming with HTTPS to an external address. Then that's going through Nginx that handles the SSL termination, and that's then forwarding the information to the legacy server. Then the other pattern, or the next pattern that the book mentions, is this ambassador pattern. So the purpose of the ambassador is to proxy or to act as a mediator between the application container and the rest of the world. In this case, we can see that the application container forwards a request to the ambassador, and then the ambassador contacts the outside world. In this case, it mentions 3 examples. So adding support for sharded Redis, adding service discovery, and also adding request splitting with A/B testing. So the idea here is that we could have, we can think about, let's say for the Redis example, is that we have a container that exposes the similar interface to Redis. Then the application container would contact this container using the same API, and the ambassador would select to which shard the request should be forwarded to. So this is again something that we could implement, deploy there, and implement it like this. Or as the book mentions, and this is where the trade-offs appear. So it's certainly valid to do it like this, but it's also valid to do it as an external service, right? To have a load balancer, and the load balancer selects the appropriate shard. So it's not entirely clear when to select one or the other. The book mentions something about what's the scale of the applications that you are running, and also mentions that having a load balancer means an extra service that you need to monitor, that you need to inspect, which I would say, well, we also need to maintain and monitor the ambassador. So it's not a clear cut. It has its use case nonetheless, like it mentions. So for example, for request splitting, maybe we can do some A/B testing. So if we can think about it like this again, we could deploy an ambassador to different services. Let's imagine a service that has 10 replicas, and we deploy an ambassador to each one of them. We can say that at least to 2 replicas, we configure that the ambassador needs to go to a separate service. That's the B service, and we can measure the activity of this A/B experiment or this A/B testing without modifying how the routing would work. This is something similar to what Istio does. So Istio provides an Envoy proxy that it's also a sidecar, which I'll mention in a moment. But it's a way of doing A/B testing or canary releases. So it has some functionality that's already implemented in some frameworks.
Does anybody have Istio running the project? Just link it in, I guess.
So yeah. So then the next pattern is the adapter pattern, and this is to adapt an interface to another. So one way to think about it would be to add Prometheus support to an existing application. So I think that it mentions something about, although I'm not sure if that's still the case, that we have Redis, for example. Looks like this guy loves Redis, and Redis doesn't offer support for Prometheus. It offers support for something else. So we could deploy an ambassador that translates one API, so the internal API to the Prometheus API. Then also talks about normalizing logs or adding rich health check monitoring. Like let's say we have a MySQL database, and instead of just with Kubernetes just checking on the health check endpoint, we can have a more elaborate container that I don't know, executes a query or does some extra checks on SQL to expose it to Kubernetes. So the key points on this section is that we can split containers, as I mentioned, in different containers to improve productivity. So we have different teams maintaining these library containers. But we have to mind the trade-offs. So this is not something like, oh yeah, okay, everything should be a sidecar. If we have, let's say, something orthogonal to the application, because obviously there are different ways of implementing. There is, let's say, for example, language support. We most of us deploy Java applications, and we wouldn't deploy a sidecar implemented in Java. Maybe the right way to go about would be to implement a sidecar in Go or Rust or a compiled language that has a smaller memory footprint, so it doesn't bother the container that much. So there is also kind of like still an advantage of saying, hey, I don't want to implement this as a sidecar or as an adapter. I want to implement this as part of my service, so it can piggyback on the resources that you're already giving the pod. So that's important. So once we start rolling out these kind of patterns, it's important to parameterize and document our containers or our images. So this is important, obviously, because the moment, and also defining a stable API, because the moment that we roll this out, this needs to be usable for people. And the only way to do it is, well, by understanding what they are doing. One critique that I have with this, besides, well, mentioning the trade-offs that the book doesn't go about, let's say implementation-wise, is that sometimes these patterns feel a bit too similar to each other. So maybe we could have a proxy that also works as an ambassador or an adapter. So it's a bit sometimes it's a bit hard to grasp or to understand. Hey, where does this fit here? As I mentioned, we have Istio that has Envoy proxies or Istio sidecars, and they could also work as ambassadors. So my take on this is that we don't really need to hang up on the naming per se, even if that's one of the purposes of the pattern. It's more like, okay, this is a new tool that I can consider when I'm implementing the service or implementing some application. The next section talks about servicing patterns. So this goes more about one step further or one level up, where we not only consider a single application or a single node, we start considering how we deploy our entire system and things more about in terms of microservices. In this case, what we have is we have 4 patterns. So we have replicated load balance services, sharded services, scatter gather, and function and event processing. So for replicated load services, so this is I would say the oldest trick or the oldest design that we know of, is that whenever we want to achieve scale, what we do is we deploy replicas of the same application, and we put a load balancer in front. So by doing that, we can serve more more users. Depending on the service that we need, or sorry, the service that's behind the load balancer, we have different load balancing strategies. So, for example, for a stateless service, we can use a round robin strategy. So it doesn't matter, like one service, any service, any replicated service can handle any request. Whereas if you have a stateful service, let's say kind of like a web shop application, where where a user adds items to its shopping cart, and that shopping cart is stored in session attributes, not on cookies, but it's stored in the service. Then we use some kind of session stickiness, so sticky sessions on the load balancer to always target the same replica for the same user. Yeah. So for example, what we can do is we can think about adding a caching layer. So in this case, the book goes about and explains kind of like step by step that we could deploy a caching layer to a service by deploying an ambassador, right? We can instead of using something like Caffeine or some external service like Memcache or Redis, we could deploy as an ambassador, right? We can say, hey, you act as a cache, and whatever request comes in, I see if I have it on my cache, and if it's a miss, I go and check the container. Obviously, this is not recommended at all, because, so even if we can think about it, it's not recommended, because that means that depending on the service, different ambassadors could have the same cache data, right? Because, well, every service can, every request can be targeted to any service, so they could eventually load the same key. So what it goes and says, hey, what we can do is we can actually add a caching layer, so we can have a load balancer and then replicate the cache, not only replicate the applications, and based on those caches, if there is a miss, we talk with the replicas, and then we share the load within the cache, between the caches. But obviously, let's say we can also, or the book mentions, is that we don't need to stop there. So ideally, we think about, okay, here's a load balancer and here's an application. We can have more levels of load balancing. So let's say that we want to have rate limiting. The way that we can do that is by having a load balancer pointing to Nginx. So Nginx is also replicated and is acting as way to control the rate limit. Then that goes into the load balancer that I showed in the previous slide, going to the cache and going to the replica. So obviously this is something that we could incorporate in each one of the replicas. So each one of the replicas could have rate limiting algorithm and a cache and whatnot. But again, this goes to think about that maybe this is an orthogonal concern, or is some separation of concern that the application shouldn't be having to deal with. So this could be something that is deployed at a higher level, and the distributed application, or the distributed system, sorry, could take care not only of, let's say, caching, could also take care of rate limiting, not only for this application, but for any that is deployed in the system. Then we have shards. So if we thought about load balancing or replicated applications as a means to achieve scale. So one thing that you see in applications such as Kafka or Cassandra, anything that is distributed, the way that they achieve scale is by replication and by sharding. So sharding is whenever we have a data set that is too large to fit in one machine. So what we do is we split that data set so it can be processed by different machines. If someone wants to access the data for a particular shard, then that request is sent to that shard. Another example of this would be partitioning on a vertical or horizontal partitioning on a SQL database that we split the data depending on well, certain criteria. In this case, we can see that a replicated service where we have 3 instances, any request A, B, and C can go to any replica, but whenever we have a sharded service, request A can only go to 1, request B can only go to 2, and request C can only go to 3. So that's basically the difference. Then we have scatter gather. So this is how we deploy a system that accepts a request and then splits that request in different worker groups, or we'll say, or worker service groups, and then it gathers the information back to return to the application to the request to the user. This feels a bit similar to MapReduce, and yeah, it's basically that, but deployed as a service instead of. So usually, whenever we are doing MapReduce, that works as some work that, let's say, a Spark application is meant to run to process some data. So it does the map to different operations and then does a reduce, and that's it. It stops. But in this case, this pattern works forces us to think about if I want to design or architect an application or a system that that needs to work in this way, needs to split the application in a map way. It can do it like this. One thing that mentions is that if we start to think about SLAs of our services, the SLA is compounded across all instances, because let's say in this case what we are doing is we're scattering a request in different nodes, and if one of those fails, we have to, let's say, compound it with all the other services that may have not failed. Then also talks about function and event-driven processing. Doesn't go in too much detail. Like I'm not sure if by the moment that the book was being written, this was still too new. But basically, the purpose of these events, or sorry, these patterns, is that to take advantage of this function as a service. So in a sense, is that each application, if we can call it that way, it's an application that's run based on an event from something. Let's say a webhook that's triggered, and then the function is executed. There are 2 patterns that this book mentions. So the one of them is the decorator, and the other one is the event-driven pipelines with functions. So the benefits from this is that we can have more granular building blocks, right? Like a container is already more granular than maybe, or a microservice is more granular than a monolith. A function could be even more granular, could be doing only one thing. So that's also something that mentions as good, like it's quite focused, does one thing and only one thing. It also has a stateless execution, so it's easier to reason about. We don't have to keep, let's say, internal state in memory, or let's say, what doesn't happen between one request and the other. We can treat this in isolation. And it's not entirely always like this, but it also mentions that it's easier to scale and deploy. Mentions that, let's say, functions are deployed with only with code, and I'm not sure if that's really the case. Like functions could be deployed with a compiled application, right? Then some challenges. Even if we have some stateless execution, the lack of state of a function is a problem, right? Usually, whenever we think about a service, we think that there is some state involved in that service, and we can act on the accumulated state so far. Well, we cannot do that with functions. So depending on what we need to do, maybe we can consider it. Then, obviously, as any event-driven pipeline, it's harder to debug, right? Because now we cannot jump into one container and read the logs or let's say attach a debugger to different things. No, this works by being executed based on an event, and as soon as that event is processed, then the function exits and we are done. So it's harder to debug. Yeah, we can maybe connect it to Fluent or to some log aggregator, but still, it's harder to debug. Let's say we cannot attach a debugger if we would want to do it. And obviously, it's not good for background processing. Maybe, let's say, cost-wise, mentions that, well, this is something that if we want to use functions, we need to be wary of. Like, let's say, whenever we deploy a service, the cost of that service, if it's used all the time, can be cheaper than deploying a function all the time or a long-running function. So it's something to consider. Also, one of the challenges that sees with harder to debug is that maybe we have a function called A that calls another function called B. Then that function called B calls function called C, and the function called C calls function A again. So creating a loop. So this is something that could happen depending on which are the teams that maintains these different functions. So that's also could be hard to spot. Is something that has to be taken into account when designing or using functions. Yeah, so I think I skipped the decorator pattern. Oh yeah, sorry, I skipped the decorator pattern. So usually what mentions about this is that we could deploy a function that acts as a decorator to a request. Maybe what we have is we have a long-running service, and we want to decorate by a request or a response by adding some information on top of that, whatever we need to do. So what we can do is we can deploy this decorator as a function. So instead of the service being connected directly with the request, we could have this function acting on the request, calling the service, receiving the response, and returning the response back to the user. So in that link, it would decorate the request or the response, whatever it needs to happen. Yeah, so for this section, as I mentioned, so scale is achieved through replication and sharding. That's how things are. This is the get to go whenever we want to achieve scale. Something that puts emphasis is that, let's say, for SLA, it's important to think about that if we want a 999 SLA, by definition, we need to deploy a service within 3.6 seconds. So that's the time that needs to be that the application needs to be stopped or needs to be unresponsive to achieve 999. So it's very.
But it's only if you measure as your SLA per hour.
Yeah, yeah. So it's better to have two instances, let's say. So let's say at least have some sense of replicas, so we can swap one replica at a time, and then do a scale rollout, a rolling scale. Sorry, a rolling scale.
So I think normally you measure SLA in larger.
Yeah, you could.
Periods like
yeah.
a month, and then 99.9 is 40 minutes.
Yeah, yeah. So I think that this is talking about hours. Yeah. Then also, well, one thing that mentions is that we don't have to think about replicas and shards as being multiply exclusive. We could have a shard that maybe is a hot shard, a shard that is target multiple times. We could replicate that and have multiple replicas of one shard to account for the bigger load that happens at that moment. And yeah, and also, well, don't overhype functions. Consider the trade-offs and especially the cost on the on the cloud provider. And finally, it talks about computational patterns, and this talks about 3. So the difference between services and batches, as I mentioned with MapReduce, is that batch jobs would take some input, would be executed, and then they would stop. They wouldn't keep running. This would be something like, let's say, maybe some reporting that happens at the end of the day or at the end of the week, and then they dump the result in a database or whatever. So in this case, it talks about three services. Three patterns. So the work queue, the event-driven batch processing, and the coordinated batch processing. So usually whenever we think about a work queue, is that we have work items, we have a work queue manager, and then that work queue delegates these work items to different workers. Then what we have is the idea behind this, or what is trying to expose in these last sections, is that if we would want to, we could implement a generic work queue, or we can think about implementing a generic work queue with some library containers. So let's say maybe by running some ambassadors as well. I'll show you in a moment. But yeah, this feels a bit too abstract. Something that maybe we don't need to do. Maybe we can rely on an existing solution instead of rolling out a thing for ourselves or by ourselves. But maybe this is more like something working at a company that offers solutions like this would think about, or should think about. So in a sense, the idea is that we can implement these utility containers as being able to spin different workers, right? So these we will have work items that would go into a container group, the work queue manager, so the one getting the work items, could have a stable API saying, hey, I process my data from, I don't know, or I process the work items from somewhere, and then the ambassador could fetch some information or execute or spin the containers by, I don't know, using some kubectl API. Then also mentions the event-driven batch processing. So this is similar to scat. This is similar to the scatter and gather, but offering more complex operators. So the idea is that once we have our work queue, what we could do is we could start implementing different patterns of how the work queues operate. So what we can do is we can have something like a copier or a filter or a splitter or a sharder or a merger. So this offers different features depending on the work items. So for example, the copier would duplicate a work item but delegate them to different queues, or the filter will take the work item and ignore it. So for example, it says that it mentions this idea of a work item could be a user registered into a system, and the copier could take that work item and it could send it could duplicate that into another queue. The queue would be send an email queue, and then another queue send promotions or whatever. So it shows some examples. Then the same thing happened with the splitter. Like it would delegate depending on the kind of work. Let's say if it has to send an email, or it has to send an SMS on a single on a two-factor authentication. This would let's say split the work depending on the type that the user has selected, and so on. It goes and shows different patterns. And it also talks about like this coordination between batch processing. So like once we have all these work items, how do we pull them all together if that's something that we need to do? And it mentions two patterns, so join and reduce. So join would be something similar to thread.join that we have on Java. So meaning that it It doesn't produce any output until all the data is available. So it kind of like blocks the output until data is available. And then we have reduce that doesn't wait until all data is available, but it can produce maybe intermediate solutions, or it would do some work while it's waiting for the work to be completed. So yeah, basically that's the key points is that we can build work queue systems to take care of batch background work, and these queues can be implemented with different patterns. My critique on this is that so this section especially, but also maybe a bit the previous one, is that it all feels too abstract, and it doesn't offer like key leverage on, okay, yes, this is a great idea to implement here or to implement there. It's just, let's say, some concepts that that we can think about and we can discuss with colleagues and maybe come up to an understanding of, okay, yeah, here we need a work queue, but we are not going to implement our own work queue. We are going to use something like Kafka to define the queue, and we are going to use these patterns within the organization. Like we are going to have a splitter defined with this component, with this container, and work not so much on an abstract scale, but well, more concrete, more like something that we can understand. But I understand like the book needs to offer some kind of abstraction, needs to like relate to these loosely based examples, so it can be applied to more than just that thing. So that's why I feel like the first section where it goes and talks about the single node patterns, where you can split a container and add sidecars on ambassadors, feels more interesting because it feels more applied, something that we could all do. So yeah, that's basically the book. Thank you.